Good afternoon or good morning or have a good day, everyone. This is ESci 114 Laboratory Exercise number 4, Masses and Springs. So this lecture video is specifically for those students taking ESci 114 with offering number A154. To be updated with more videos, please click the like and subscribe buttons below. So the underlying principle behind the masses and springs laboratory exercise number 4 is the motion of a spring on a mass. But before we do that, or before we proceed with our discussion, let me first update you with our timetable for the submission of your activities. So again, we only have 6 laboratory exercises for ESci 114, and now kinahanglan naana mo sa exercise number 4. Unfortunately, only few students have already completed exercises 1, 2, and 3. And most of you has not submitted any laboratory exercise yet. So please make sure nga makasubmit na mo sa inyong lab exercise before our deadliest deadline on December 3. You still have 1 month to go. So throughout this lecture video, I will be showing to you 3 problem-solving questions that you can solve at home later on. And since this is physics, do not remember, please always remember to not forget the units. So to start, we have to define first some basic definitions in physics. So first, we have what we call as the periodic motion. So this is the motion repeated in equal intervals of time. So if actually I cannot use my pen tab right now, but if I can use my pen tab, I can demonstrate to you that that if we will stretch the mass on a spring, then we will create an initial displacement that will make our mass to move in a periodic motion. So as you can see from the illustration, through time, your mass will reach its maximum state or maximum position, that is the amplitude. After reaching the amplitude, it will go down to its equilibrium state, and it will go further down to its minimum location or position, which is also the same length as the amplitude, and it will go back to its equilibrium position. So that is one complete cycle, and that one complete cycle is called a period, and the number of period per unit time is called the frequency. So from the definition, we can know that period, or in symbol, period is written in capital letter T. Period is just the reciprocal of frequency. So with that, we can relationship between period and frequency, we can deduce that the period of the Earth's orbit is 1 year, and its frequency is 1 orbit per year. On the same scenario, or on the same logic, a tuning fork might have a frequency of 1,000 cycles per second, and reverse or inverse of period is frequency, and a period of 1 millisecond or 1,000 of a second. So one example or special case of periodic motion is the simple harmonic motion. Okay, so a vibrating object is wiggling about a fixed point, as what you can see on your screen. Like the mass on a spring in the animation, a vibrating object is moving over the same path over the course of time. Its motion repeats itself over and over again. If it were not for damping, usa may meaning anang damping. Damping is ang kanang paghinay sa oscillation. It will stop or it would tend to decrease the oscillation. So that is called damping. So if it were not for damping, the vibrations would endure forever, or at least until someone catches the mass and brings it to rest. So naagihapon na ang application sa first law of Newton. Again, usa ganito ang first law of Newton. An object will continue to be moving or continue to remain at rest until an external force will act upon it. So the mass here, the mass on the spring, not only repeats the same motion, it does so in a regular fashion. So the time it takes to complete one back and forth cycle is always the same amount of time. So for example, if it takes the mass 3.2 seconds for the mass to complete the first back and forth cycle, then it will also take 3.2 seconds to complete the 7th back and forth cycle and the 10th back and forth cycle and the nth back and forth cycle. So it's like a clockwork. It's so predictable that we can use formulas. So later on, I will be introducing you to the formulas that we can use to predict or to solve for the to solve problems related to the periodic motion, specifically the periodic motion of a mass on a spring. So in physics, a motion that is regular and repeating is referred to as a periodic motion. Most of the objects that vibrate do so in a regular and repeated fashion, and their vibrations are called periodic. So naatay ginatawag nga sinusoidal nature of vibration. Suppose that a motion detector was placed below a vibrating mass on a spring in order to detect the changes in the mass's position over the course of time. And suppose that the data from the motion detector could represent the motion of the mass by a position versus time plot. So that one is presented or can be seen on the graph on your screen. So that graph, you can locate the x-axis, or you can locate the time on the x-axis and the position of the mass on the spring on the y-axis. And for our discussion, we labeled several points on the graph to assist us in the follow-up discussion. So one obvious characteristics of the graph has to do with its shape. I believe most of you have encountered this shape of this graph from your experiences sa inyong Calculus 1. So the graph has the shape of a sine wave. That's why it is called sinusoidal. That's why naay sinusoidal nature ang vibration. So if we will plot the equation y is equal to sine x on a graphing calculator, so a graph with the same shape would be created. The vertical axis of the above graph represents the position of the mass relative to the motion detector. A position of about 0.6 meter or 0.6 centimeter above the detector represents the resting position of the mass. So, the mass is vibrating back and forth about this fixed resting position over the course of time. And there is something sinusoidal about the vibration of a mass on a spring. And the same can be said of a pendulum vibrating about a fixed position, or of a guitar string, or of the air inside a wind instrument. So all of those are vibrating and have a sinusoidal characteristic. The position of the mass is a function of the sign of the time. Another obvious characteristic of the graph may be its periodic nature. The motion repeats itself in a regular fashion. Time is being plotted along the horizontal axis, so any measurement taken along this axis is a measurement of the time for something to happen. A full cycle of vibration might be thought of as the movement of the mass from its resting position at A to its maximum height at B, back down past its resting position at C, or equilibrium position. A while ago, I mentioned the word equilibrium. So that is the resting position also at C, and to its minimum position at point D, and then back to its resting or equilibrium position at point E. Using measurements from along the time axis, it is possible to determine the time for one complete cycle. The mass is at position A at a time of 0 seconds, so magsugod ta og time 0, and completes its cycle when it is at position E at a time of 2.3 seconds. So, therefore, it takes 2.3 seconds to complete the first full cycle of vibration. Now, if the motion of this mass is periodic, meaning, so ganito yung meaning sa periodic, regular and repeating, kanang ang iyang damping is very minimum to 0, then it should take the same time of 2.3 seconds to complete any full cycle of vibration. The same time axis measurements can be taken for the 6th cycle of the vibration, which is at point, 6th cycle is from point U, V, W, X, Y, kaning last nga cycle or last nga period sa graph. So in the 6th full cycle, the mass moves from a resting position U up to point V, back down past point W to point X, and finally back to its resting position point Y in the time interval from 11.6 seconds to 13.9 seconds. This represents a time of 2.3 seconds to complete the 6th full cycle of vibration. As we can see, the two cycles, the 1st and the 6th cycles, are identical. Other cycle times are indicated in the table shown on your screen. And by inspection of the table, we can safely conclude that the motion of the mass on a spring is regular and repeating. Therefore, it is clearly periodic. However, there is a small deviation from 2.3 seconds in the 3rd cycle. Now, this can be accounted for the lack of precision in the reading of the graph. So now, let us discuss the basic definition and principle of Hooke's law. So we will begin our discussion with an investigation of the forces exerted by a spring on a hanging mass. Consider the system shown on your screen with a spring attached to a support. The spring hangs in a relaxed and stretched position. If you have to hold the bottom of the spring and pull downwards, the spring would stretch. If you were to pull with just a little force, the spring would stretch just a little bit. And if you were to pull it with much greater force, the spring would stretch a much greater extent. So the question would be, exactly what is the quantitative relationship between the amount of pulling force and the amount of stretch? Now, to determine the quantitative relationship between the amount of force and the amount of stretch, objects of known mass could be attached to the spring. So for each object which is added, the amount of stretch could be measured. The force which is applied in each instance would be the weight of the object. And after that, we can use regression analysis. Or we can perform regression analysis of the force stretch data in order for us to determine the quantitative relationship between the force and the amount of stretch M. Kanang naa sa third column. So the data table below shows some representative data for such an experiment. So our masses, we put an interval of 50 and some are 100 grams interval. And by plotting the force stretch data and performing a simple linear regression analysis, I believe you have already encountered during your senior high school days how to perform a basic linear regression analysis. So by doing so, the quantitative relationship or equation can be determined. And the plot from our previous data is shown here. So a linear regression analysis yields to the following statistics. So the slope of the line, so the slope of this line is equal to 0.00406 meter per Newton, or run over rise. Rise over run, sorry. Rise over run. The y-intercept is 3.43 times 10 to the negative 5, or it is very close to 0. As you can see from the graph, it is almost passing through the y-axis at point 0, or at the origin of the graph. The regression constant is 0.999, which is almost equal to 1. And by using these statistics, we can now formulate, or we can now write the equation of the line, which is equal to stretch is equal to 0.00406 times force plus the slope, plus the y-intercept, which is 3.43 times 10 to the negative 5. Okay, the fact that the regression constant is very close to 1, okay, 0.999 man siya, indicates that there is a strong fit between the equation and the data points. This strong fit lends credibility to the results of the experiment. This relationship between the force applied to a spring and the amount of stretch was first discovered in 1678 by English scientist Robert Hooke. And as Robert Hooke puts it, ut tensio sic vis. So translated from Latin, this means as the extension, so the force. This quantitative relationship between the force and the stretch is referred to as now as Hooke's law, and is often reported in different references as F spring is equal to negative K times X, wherein your F spring is the force exerted upon the spring, the X is the amount that the spring stretches relative to its relaxed position, and K is the proportionality constant, and often referred to as the spring constant. The spring constant is a positive constant whose value is dependent upon the spring which is being studied. So for example, you have a stiff spring, kanang gahion nga spring. So it would have a high spring constant. This is to say that it would take a relatively large amount of force to cause a little displacement. So kung gaya ang spring, you still have to pull it very hard. You have to exert more force in order for it to have displacement. So the unit of force or the unit of spring constant is Newton per meter, because basically we know that the unit of force is Newton and the displacement or x is in meter. So therefore, your K or spring constant is in Newton per meter. However, sa atong formula, we can see nga naatay negative sign. This is an indication that the direction that the spring stretches is opposite the direction of the force which the spring exerts. For instance, when the spring was stretched below its relative position, x is downward. The spring responds to this stretching by exerting an upward force. So that upward force is what we call as the, later on we will discuss that, but I forgot the term, restoring force. Now that is called the restoring force. The x and the f are in opposite directions. Now, so earlier, we learned that an object that is vibrating is acted upon by a restoring force. The restoring force causes the vibration, the object itself that is vibrating to slow down as it moves away from the equilibrium position and to speed up as it approaches the equilibrium position. So it is this restoring force which is responsible for the vibration. So what is the restoring force for a mass on a spring? So we will begin our discussion of this question by considering the system in the diagram on your screen. So it is an air track and a glider. So the glider is attached by a spring to a vertical support. There is a negligible amount of friction between the glider and the air track. So dili lang nato i-consider ang effect of friction for us to fully understand or to fully learn the relationship between the force and the mass on the spring. So as such, there are three dominant forces acting upon the glider as shown in the free body diagram. So we have the force of gravity, which is a rather predictable force both in terms of its magnitude and its direction. So the force of gravity is like the weight, that is the mass times g, or mass times acceleration due to gravity. We also have the F support, or the support force, which balances the force of gravity. It is supplied by the air from the air track, causing the glider to levitate about the track's surface. The final force is the spring force, F spring. And as discussed a while ago, the spring force varies in magnitude and in direction. Its magnitude can be found using usang formula. So we can find its magnitude using Hooke's law. Its direction, however, is always opposite the direction of the stretch and towards the equilibrium position. As the air track glider does the back and forth, the spring force, or F spring, acts as the restoring force. It acts leftward on the glider when it is positioned to the right of the equilibrium position, and it acts rightward on the glider when it is, on the other hand, positioned to the left of the equilibrium position. Okay, so let's suppose that the glider is pulled to the right of the equilibrium position and released from rest. So the diagram below, or the diagram on your screen, shows the direction of the spring. Kung asa padulong ang spring after nato gi-release ang glider or from its equilibrium position. So we have 5 different positions: A, B, C, D, and E. So as the glider moves from position A, which is the releasing point, to position B, and then to position C, the spring force acts leftward upon the leftward moving glider. As the glider approaches position C, the amount of stretch of the spring decreases and the spring force decreases. This is consistent to the Hooke's law. Despite this decrease in the spring force, there is still an acceleration caused by the restoring force for the entire span from position A to position C. At position C, the glider has reached its maximum speed. Once the glider passes to the left of position C, the spring force acts rightward. During this phase of the glider cycle, the spring is being compressed. The further past position C that the glider moves, the greater the amount of compression and the greater the spring force. This spring force acts as a restoring force, slowing the glider down as it moves from position C to position D and to position E. By the time the glider has reached position E, it has slowed down to a momentary rest position before changing its direction and heading back towards the equilibrium position. During the glider's motion from position E to position E to position C, the amount that the spring is compressed decreases and the spring force decreases. There is still an acceleration for the entire distance from position E to position C. At position C, the glider has reached its maximum speed. Now, the glider begins to move to right at point C. And as it does, the spring force acts leftward upon the rightward moving glider. This restoring force causes the glider to slow down during the entire path from position C to position B to position E. So a while ago we discussed that the variation in the position of a mass on a spring with respect to time, so we discussed that a while ago, and at that time it was shown that the position of a mass on a spring varies with the sign of the time, or sign t. So we also discussed this that the mass that was vibrating up and down while suspended from a spring. So now this is the diagram wherein we label the position of our discussion of the restoring force. No? As we can recall from that discussion that positions A and E were positions at which the mass had a zero velocity. Position C was the equilibrium position and was the position of maximum speed. If the same position, if the same motion detector that collected position time data were used to collect velocity time data, then the plotted data would look like the graph that is colored blue. Observe that the velocity time plot for the mass on a spring is also a sinusoidal shape plot. The only difference between the position time and the velocity time plots is that one is shifted 1/4. So na siya 1/4 of a cycle nga difference. Also observe in the plot that the absolute value of the velocity is greatest at position C. So this corresponds to the equilibrium position. The velocity of any moving object, whether vibrating or not, is the speed with a direction. So the magnitude of the velocity is the speed. The direction is often expressed as a positive or a negative sign, because we all know that velocity is a vector quantity which contains both the magnitude and direction. In some cases, the velocity has a negative direction, or katong case na to ganiha nga ang glider is moving padung dito sa left, and its velocity is plotted below the time axis. In some cases naman po, the velocity has a positive direction, katong atong glider ganiha that is moving to the right, and its velocity is plotted above the time axis. We can notice now that the velocity is 0 whenever the position is at an extreme. This occurs at positions A and E, when the glider is beginning to change direction. So just as in the case of a pendulum motion, the speed is greatest when the displacement of the mass relative to its equilibrium position is the least, and the speed is least when the displacement of the mass relative to its equilibrium position is the greatest. Now, let's go to energy analysis. On the previous discussion, or as you might have already discussed sa inyong lecture classes, you might have already discussed energy analysis for the vibration of a pendulum. No? So, energy can be kinetic. So, there are different types of energy. So, one of those is the kinetic energy. So, this is the energy possessed by an object due to its motion. It is a quantity that depends upon both the mass and the speed. And if we will write that in formula, we'll have Ke is equal to 1/2 mv squared, or kinetic energy is equal to 1/2 times mass times the square of the velocity. So from our equation, we can say that the faster an object moves, the more kinetic energy that it will possess. We can combine this concept with the discussion a while ago about how speed changes during the course of motion. This blending of the concepts would lead us to conclude that the kinetic energy of the mass on a spring increases as it approaches the equilibrium position, and it decreases as it moves away from the equilibrium position. So this information is summarized from the table as you can see on your screen. So kinetic energy is only one form of mechanical energy. The other form is potential energy. And by definition, it is the stored energy of position possessed by an object. So basically, this is based on the position of, this is dependent upon the position of the object. The potential energy could be gravitational potential energy, in which case, the position refers to the height above the ground. And on the other hand, this could be elastic potential energy. In this case, the position refers to the position of the mass on the spring relative to the equilibrium position. Sa atong ganiha sa atong air track glider, there is no change in height. So therefore, ang atong gravitational potential energy does not change. This form of potential energy is not of much interest in our analysis of the energy changes. Because ang ato adire nga gina-consider nga potential energy is the elastic potential energy. So the amount of elastic potential energy depends on the amount of stretch or compression of the spring. So as you can see from our equation of the potential energy, we have 1/2 kx squared, wherein our k is the spring constant and x is the distance that the spring is stretched or compressed relative to the relaxed unstretched position, or what we call as the spring constant. So when the air truck glider is at its equilibrium position or position C, it is moving its fastest, no, as atong gi-discuss a while ago. At this position, the value of x is pila man? How many meters? So the value of our x is 0. Again, the value of our x at equilibrium position is always equal to 0. So the amount of elastic potential energy at the equilibrium position is always 0 joule. Again, FYI pala, ang unit for potential energy or for energy in general is joules. This is the position, ang kaning equilibrium position wherein the potential energy is the least. So when the glider is at position A, the spring is stretched to the greatest distance and the elastic potential energy is at its maximum. A similar statement can be made for position E. Same ra sila, maximum ang ilang potential energy. Since the spring stretches as much as it compresses, the elastic potential energy at position A is the same as at position E. At these 2 points, A and E, the velocity is how much? The velocity is 0 meter per second and the kinetic energy is 0 joule. So, just like the case of the vibrating pendulum, a vibrating mass on a spring has a greatest potential energy when it has the smallest kinetic energy. And it also has the smallest potential energy at position C when it has the greatest kinetic energy. So, muna siya ang ginapakita sa atong illustration. So, here I am just showing to you the screenshots of every positions and the amount or the status of the kinetic and potential energies at each position or each transition. Yan. So when we are conducting energy analysis, a common representation is an energy bar chart. An energy bar chart uses a bar graph to represent the relative amount and form of energy possessed by an object as it is moving. So it is useful conceptual tool for showing what form of energy is present and how it changes over the course of time. So the picture you can see on your screen is an energy bar chart for the air truck glider and spring system. So the bar chart reveals that as the mass on the spring moves from A to B to C, the kinetic energy increases and the elastic potential energy decreases. Yet, the total amount of these two forms of mechanical energy remains constant. Because from the law of conservation of energy, energy can neither be created nor destroyed. So, some forms of energy, so like this one, the mechanical energy is being transformed from potential energy to kinetic form, yet the total amount is being conserved. Now we will learn how to analyze vertical and horizontal spring mass systems. So the derivation of this formula, T is equal to 2 pi times square root of m divided by k, is shown on your laboratory guides. So here, T represents the period, m represents the mass, and k represents the spring constant. So both vertical and horizontal spring mass systems without friction oscillate identically around an equilibrium position if their masses and springs are the same. For vertical springs, however, we need to remember that gravity stretches or compresses the spring beyond its natural length to the equilibrium position. After we find the displaced position, we can set that as y is equal to 0 and treat the vertical spring just as we would a horizontal spring. So from the picture, we can see that the resting position of a vertical spring and the equilibrium position of the spring masses after it had stretched a distance d. So that is all for our discussion for the physics behind experiment number 4. So I have prepared here 3 problem solving that you may try to solve at your home. No? This will also serve as your review for our upcoming long exam sa laboratory on December 3, which we can also move to December 10. No? Basin ma-move nato on December 10. So actually, a while ago, I was practicing to solve this one. However, my pen tab is not working. So basin mag-share na lang po ko video using my pen tab in solving these problems. So you may pause the video and solve this problem by your own. Okay? But before you do that, the underlying formula that we can use this here is the Hooke's law formula. So given the force, again, this is what I always tell my students, that during exam, if there are problem solving, you have to follow the correct procedure in solving a problem solving. So first you have to write what are the given. 1 is given, 2 required, then before you write your solution or your working solution. So under your working solution, you may first write your working equation. So for this one, your working equation is Hooke's law, which is force is equal to negative k times x. I will share to you another video of my actual solving of this problem. But for now, as what Robert Hooke said, potentio sic vis. So as the extension, so the force. Force and stretch are proportional or directly proportional to one another, such that if you double the force, the amount of stretch will double. So the answer is 32. Sa atong exam, sa long exam, please make sure that you write the given, the required, before you write the solution for our problem solving exams. Another question for this one, the working formula is ang katong T is equal to 2, kanisiya, 2T is equal to 2 pi times square root of m over k. But even though we do not use, we just analyze the 2 cases, we can identify that the answer or the one with a higher frequency is case B. But again, for your exam, please make sure that you write first the given, the required, and followed by your solution. For this third, since we are almost running out of time and we have limited time, but again, I will also share to you my computation for this one. Pero kumpleto naman siya, no? So, muna siyang akong gusto nga makita sa inyong final exam. na ay given, na ay required before you write your solution. And these are my references for my discussion today. So, thank you, and don't forget to click like and subscribe to my YouTube channel. And also click the notification bell so that every time magpo-post ko video, mano-notify mo. Thank you and good afternoon.